So here I show supersonic Mach 1.4 flow around cylinder in 2D. So initial mesh is really coarse, and by refinement we do simple projection to get rid of geometrical error. So this one is primal solution. This is Mach number in colors, and I also put this sonic line. So as I said before, sonic line, it's a line where the transition from subsonic to supersonic and vice versa goes. And in this line, there is a big jump in solution, and we have like a sharp shock. So in fact, we see that this one is corresponding dual problem, dual solution. In color, I put dual pressure, and in curve contours density and also velocity, dual velocity in arrows. So velocity is like playing around cylinder, and it indicates which part is important to resolve to get accurate drag force. And if you notice here, so this Mach sonic contour, it starts in the beginning from here and it moves to this direction. But this distance is fixed because it stays constant after some time when everything gets stabilized. So in this, it seems sonic contour, it's really sensitive to get accurate drag for the compressible flow. And also it indicates some parts which will be resolved by the method. Okay, so from primal solution, residual is really high along the sonic contour, sonic line, because of this sharp jump in shock. Okay, so this one is like residual based adaptivity. It is another Mach number, but I just it will look almost the same. But if you do residual based adaptivity to resolve let's say drag, the algorithm always follows shock, because shock is always high. If we put a lot of mesh, it will be even steeper and it will be even higher. But the sensitive part for pressure distribution, which goes along this boundary, it's not resolved, which has really high contribution for drag force. So like I didn't get convergence after even 25 times adaptive refinement. It was really like far away from the actual convergence. But I run similar problem with duality based adaptivity. So here you see that I plot 10 contours of Mach number, so it shows sensitive parts of the compressible flow. Mach number in primal solution, and also I show this mesh after adaptation. So we solve primal, dual, we do adaptation. And here you see that close to the boundary, here we have Mach stump. So also the part where there is a transition from supersonic to subsonic and vice versa. The pressure changes, and adaptive algorithm also focuses to resolve and get correct change from this pressure. And here also stagnation point for pressure is really important for drag. So you see that it resolves along that one. And as I showed before, this is like sonic line which moves, and also it has like high contribution for drag. So with this one I got convergence after already 18.9. We can see that in the second decimal this drag stays in the same region, so the error goes in the second decimal. And here I compare with reference solution, which I got with many times uniformly refined the same mesh, and this one is error indicator which decays. So I did another example. It is a Mach 3 flow around the wedge. The point to run this example is that here this shock is attached to the body, and I would like to see that how the adaptive algorithm works in this case. So we didn't change anything. We just changed boundary condition and run. So this was primary equation solution marked in colors, and this one is dual solution, pressure in colors, and also arrows of velocity. I put together with Mach contour, and here we see that dual density follows a little bit shock. It seems this part has major effect for the drag, and then it goes to inflow direction. And also this area where the stagnation point is, it seems it's very important for the accurately calculating drag. So here I put adaptively refined mesh. Here also I did comparing between two reference solutions. So this first reference solution is also many times uniformly refined mesh, and second one is even finer. So we see that the difference is big, and actually it is getting closer to the result from our adaptive method. Because in this method, the algorithm automatically finds these stagnation points, also these discontinuity points. It resolves, and the effect of these singularity points in the solution gets smaller. However, in this case, it is large. So since I said we extend this duality-based adaptivity in 2 and 3-dimensional case. So this is like primarily result in 3D. This is transonic flow. Here Mach number is 0.8, and I put here dual density in 3D and dual pressure and dual velocity. So geometry is cylinder, and we have experimental data for this geometry. And so this is mesh, which is the result of adaptive method. Initially I get really coarse mesh, and here you see after 8 iterations, so the mesh get this kind of structure. So it seems it resolves only those part which is close to the cylinder and has a sensitive effect to the drag force. And here we see that the drag coefficient is getting closer to this experimental data after this 8 iteration. So conclusion. So G2 method, we showed it is simplified, as we said, stabilized method, and the method is conservative, and from the construction it is cheap to implement and extended in many dimensions. So in this work we developed a posteriori error analysis for compressible Euler equation in a full 3-dimensional case, and also time-dependent problem. So this then in future we are going to solve some applications for turbulence flow, for compressible flow, which will be extension of the work by Hoffman and Jonsson. Then of course it will be, we showed now number of examples, and we would like to have it in 3D with a lot of validation. So future, this solver, compressible solver, it is part of the unicorn, and we will keep developing it also. And so the future plan would be to couple this adaptive compressible solver with fluid structure interaction. So we have some first steps for this multi-phase flow, where we applied the Cahn-Hilliard equation with the Navier-Stokes. Then the idea would be to use compressible flow with this in multi-phase flow also in many applications. Okay, thank you.